Hello everyone. I know it's been a while, almost 24 hours since my last upload, but I really wanted to understand this problem that we're going to tackle. It's example 14 from our review slides, and I gotta say this was by far one of the most difficult ones that we had. It covers a lot, a wide variety, so this is a good question to know and fully understand before we take our exam. Just wanted to say that. In addition, the reason why it took me so long to create this video is because I wanted to make sure I understood everything with confidence to be able to explain it to you in a correct way and not just simply tell you how to get to the answer. So I'm going to in depth explain why the answers are the way they are, or how to get to the answers. Okay, so the first part says, if there is no forwarding or hazard detection, insert no-ops to ensure correct execution. By now, we've all have experience in this, so I'm sure that we can just breeze through this without any explanation. I'll simply just write it. So we'll have a first instruction, X15, X12, X11, no need for a now we need a no-op. Sorry, we need a no-op because this is being used here. So we have to make sure that it is available after the write back phase. So we're gonna insert one no-op, and that will, so if we write it, instruction fetch, instruction decode, execute, mem, which we don't use in that one, and then write back. Now we need instruction fetch, instruction decode, execute, and we need this execute to be after this write back, right? So if we insert one no-op, it will be right here. So it's at the same clock cycle, but we still need another one. So we're gonna insert another no-op, and it will be after the execute will be after the write back. Okay, so let's write in another note. Now we can load word. X13 offset 8 from the base address of X15. Then our next one, which is X12. Okay, we can go ahead and we can write load word X12 base 0, offset of 0, so it's going to be the base address at X2. Okay, and now we are going to the OR. So for OR, right, X13, we have to OR together X13 and X15. So this destination register from this load word is going to be used here. So we're going to have to make sure that there is 2 spaces between this instruction here and this OR instruction. So initially we have this one instruction, and now we need another instruction before to ensure that the execution happens after the write back of this instruction. Okay, so we're just going to insert one nope, and then we're going to easily breeze through our OR. So we'll just write that down. X15, X13, and finally we have the store word. And so the store word has a base address of X15 with a 0 offset, and we're trying to store this X13 ORed value into basically the base of the stack starting at X15. So in order to do this, once again, we have to wait 2 instructions after our OR to ensure that the write back is complete and we have the value available within X13 or within the cache X13. Okay, so now we can just write that, and there we go. That's our that is the answer for part A. Now part B, what does part B say? It says, now change or rearrange the code to minimize the number of nopes needed. You can assume register X17 can be used to hold temporary values in your modified code. So essentially we're just trying to modify the code, right? So perhaps we can move this up here and so on and so forth, right? But we have to ensure that we're getting the same values. So if we move any of the code, two things are going to happen. One, we're going to start getting the wrong values, which means we're basically rewriting new code, so that defies the law of the question. And the second one is if we move it in such a nice or correct order, we're just going to get more or the same number of nopes. So essentially it is not possible. So B, we're just gonna write D and E. Flashback to our 1013, 1014, and 2015 class. It just stands for does not exist. Okay? Now, what is part C? Part C, if the processor has forwarding, but we forget to implement the hazard detection unit, what happens when the original code executes? Okay, so this relates to one of our earlier examples, and I'm just going to have a sip of water. One moment, please. Okay, and that earlier question was specifically the one where we had the, what's it called? This relates to the one where we could not write over the memory, like we couldn't instruction fetch during while something else was writing into the memory. That one, I forget which number example that is, but it kind of relates to that one. So if the processor has forwarding, but we forget to implement the hazard detection unit, what happens when the original code executes? So essentially, let's look at what's happening. So if we have forwarding, so we have this forwarding, right? But we don't have this hazard detection unit. Okay? So if we have forwarding, we're still going to be receiving all the values from the instruction, right? So we'll still be able to send the correct values when needed. So for example, for the nope instruction here, if we move it up here, right? I'm just gonna write one diagram for us. So let me just erase it. So this is the one with this hazard right here, which is the read after write hazard. Okay? And so we're again going to have the instruction fetch, instruction decode, execute, mem, write back. Okay? And then the second one is going to be instruction fetch, instruction decode, execute, mem, write back. Okay, so since we have forwarding, right, originally what the hazard was that we need this write back value after the execute value. Okay, so that's what we needed. And since we can't go back clock cycles because it's impossible to have a value ready prematurely, so how we would forward it here is that as soon as the ALU is done adding it and it sends it to this phase, right, the forwarding unit would detect that this is the value needed, or like if it goes all the way down here, right, and then it goes up here to this mux, So the forwarding unit is smart enough, or like it has the correct logic that there would be a match within that forwarding unit, and it would be able to select that data, right? So we can essentially skip the memory phase and the write back phase. So basically what the forwarding is going to look like here is this is going to happen. So the execution is going to happen. It's going to be ready, and we'll be able to forward it to this execute. Okay, so that X15 value, or that register 15 value, will be ready to add the offset of 8.2 when it goes into the ALU. All right, so in conclusion, the code executes correctly, is what I'm trying to say. And I'm just going to read the answer. We need hazard detection only to insert a stall when the instruction following a load uses the result of the load. That does not happen in this case. But is that not what I just explained? We need hazard detection only to insert a stall when the instruction following a load uses the result of the load. No, you're right. I misspoke. It does not happen here. Why? Because X15 is an R type, or add is an R type, so the addition happens, and then we use that as the base address. Okay, perfect. Now to the hard part, to the part that took me so long to understand with confidence and be ready to explain here. Okay, so let me just clear this. Okay, and let me just set up. So, okay, I'm back. I'm ready to go. You guys won't know this, but let me just say something. This is my second take at this part because I made a extremely crucial, like I made a very bad mistake at the beginning, and I wasn't able to fix it. It would have just been too embarrassing to publish. But let's go through this again, okay? Or let's go through this for your first time, my second time. Okay, so what is the question asking? The question is asking if there is forwarding for the first 7 cycles during the execution of this code, specify which signals are asserted in each cycle by hazard detection and forwarding units. Okay, great. So, from part 3, we know that we need hazard detection only to insert a stall when the instruction following a load uses the result of the load. That does not happen in this case. So since we know that does not happen here, we don't need the hazard detection because it's always gonna have the same output for every single value. Okay? Or it's gonna have the same output for every cycle. Okay? So let me quickly explain the hazard detection unit though. It's important to understand. So what it does is it accepts inputs from the instruction here. It also has the memread as an input, okay? And it outputs either nopes or it outputs stalls. In addition to the nopes and stalls, it outputs signals to this mux. And if it does assert this mux, then it sends a 0 out. And what that 0 does is it basically inserts a stall into the pipeline. And if we recall, stalls and nopes are slightly different, but essentially they perform the same purpose. Okay, now what's important here is the forwarding unit. And so let's go over the forwarding unit. So to begin, the forwarding unit has a few inputs, okay? And so let's zoom in. So we have register 1 and register 2 as inputs. Why would we have those as inputs? Well, for example, here we have register 1 as the same as this destination register. And so inside the forwarding unit, it can tell, or it basically essentially reads them and notices that they are the same, and it will be able to assert the correct, it will send the correct signals to both forward A and forward B. Okay? In addition to that, it has some other ones. Like I said, it would notice that this destination register and this RS1 are the same, and so how would it know that this destination register is one of them? Well, that is a great question. And how it knows that is that, for example, here, that this data here, or this wire, essentially is from the write back phase. It is the destination register, and here again we have the destination register, but it's from a different phase. It's actually from the mem phase here. So this is going to be the mem dot rd. Okay, and then notice we have these two other signals. What are the two other signals? Well, they are from different stages. This one's going to be from the mem stage, and it is going to be the write back signal, or the reg-write, sorry, not the write back, reg-write, register write. And then this one is also going to be from the write back phase, and again it's going to be the register write. I know it's a little blurry, but it helps explain it. And finally, or in addition to that, the main purpose of this forwarding unit is to essentially tell this mux and this mux what to choose from. And so the three values that go into this mux are this. Honestly, I explained it better in the last video. I'm just going to use my explanation from the last video and continue on from where I was in the last video. That's actually a good way to go about this. So note here, I'm just going to write a nice. What happens is where the PC goes into the instruction memory, and it goes to this PC address inside their memory, and it gets the instructions from that, and that's all that happens in this. So forward, so like we don't need any forwarding because we're still like we're here and forwarding's here, so why would we need forwarding? Forwarding just is irrelevant. Forward A equals forward B. And at this point in time, kind of like Trump, he is irrelevant. So okay, I'll just leave it like that. Now, 2. What happens at 2? Well, let me just highlight it here to keep consistency. So the second time here, okay, for the second cycle, well, we now have the R-type instruction. The R-type instruction is going through the registers, right? And it's now starting to send some signals here. It's starting to send some signals here, some signals to the control, right? And that instruction is, basically the instruction is going everywhere where it's supposed to. And for the load, its load is going from the PC. It's in the instruction. That PC address is fetching the instruction at that PC address, and that's what's happening here. So again, we're not really, there is being some signal sent to the forwarding unit, but the forwarding unit isn't detecting anything that needs to be forwarded. So again, forward A equals forward B, and we still don't care. All right, let's begin. Cycle 3. So for cycle 3, let's think about this here. Cycle 3, we have everything once again. Cycle 3, only thing that's in execution is here, and it relies on there's nothing previous to it, so it doesn't rely on anything previous. So again, we're just going to send the forward signals as is. So forward A equals forward B, which is equal to 0. Now let's go to 4. What's happening at 4? So we'll have this, okay, and 4, notice how it relies like this. So X15, the result, the destination register is the base address for the load word. So we need the base address to add 8 to it inside the ALU, which happens inside the execution stage. So we need the result of this execution for this here execution, okay? And since we know that one of our two muxes will be required for we will have to send a forward signal to one of the two muxes. Now, which of the two muxes? That's a good question. The reason we're going to choose forward A is because forward A is we're going to choose forward A because if we recall from up here, we use the immediate gen, and the immediate gen, or the sign extension, right, because we have an 8 for the load word as the offset, it goes to one of the muxes. And using that same logic, we're going to have some immediate gen go to this mux. So forward A is, or the mux A is what will send A equals 2. And if we recall, 2 in binary is 1 0, and 1 0 says that the first ALU operand is forwarded from the prior ALU result. So essentially we're choosing this one, and if we trace it all the way back, no, 1 0 is 2, so it's this one. So yes, so we trace it all the way back, we're going to be getting the result from ALU, right? And what's right here at this junction? We know that it was the result from last time, which is the R type, so it's going to be X12 plus X11. Okay, so that's the result we needed, so that's the result we get, and we're going to take it from our top mux. Why? So we can have this essentially be X15, and this will be 8, and that's what we can send to the ALU. Okay, so that's why forward A and forward B for this one are like that. Next we'll go to 5. So what's that? Okay, I apologize with this video taking such a long time. I've been like stopping and starting and trying and retrying to make this video, because every time I get to the 5th cycle, right? The 5th cycle has the second load in its execution, and it doesn't rely on anything previous, right? So I'm pretty sure the answer is wrong, okay? So I'm going to claim that the answer for both A and forward B should be 0. Why should they be 0? The reason they should be 0 is because we need to take both of the information, or both of the data from the registers. Why? The base address is X2, and we never used X2 in any of the previous results. So because of that, like, we're taking 0, the immediate, that's from the register, and x2, and we're adding them together. So because of that, I'm claiming that forward A and forward B both should be 0. Unless anyone wants to prove me wrong, by all means, I encourage you. So let's move forward to the execution 6. Execution 6 relies on this write back and this memory. Okay, so what's at the write back at this time? Well, x15. And what's at the memory at this time? x13. So how can we claim this? Well, we can claim it in either forward A and forward B. They both have access to this result. So, I mean, the answer here is interchangeable in my opinion, unless someone tells me why it's not interchangeable. So forward A, I'm going to say we want the write back data. So how can I have access to the write back data here? Let me just erase all of this, right? So x15 is here. Okay, and we want access to this, so we can go ahead and follow the line. We go to this junction. Once we're at that junction, we can go up, and we can notice that we can get access to it for the second mux. Okay, so I'm going to write forward B equal to, I want access to that mux right there, and in order to get access for this result from the mem write back phase, or the second one, I have to write it as 0, 1. Okay, and forward A, okay, forward A, that's right here. So we have x15, now we want x13, so x13 is right here. Let me just write that. So x13 is there, and we're gonna follow that all the way around here, and then we're gonna go up. We've already used mux B, so let's go up to mux A, which is right here. And in order to select that one at mux A, we are going to write it as 1, 0. Yes, and that's our answer for 6. And finally, for the 7th stage, we're going to choose a new color because why not? This is one has been ridiculous. We'll choose a color I haven't used, red. So 7. Okay, and what's at the 7th stage? We have this execution of the store word, and that store word has a base address of x15. And again, it's in x15. I know we used it in the previous instruction, right, to go for our forwarding, but it also gets written back. So by the time that we're using it again for the second time, it's already written in the registers. So both forward, like the offset of 0 and x15, they're both from the registers. So both forward A equals 0 and forward B equals 0. I'm gonna send this to Ali in addition to the Discord, because you guys can correct me if I'm wrong, but I'm pretty sure that this is the correct way to go about it. And yeah, that's essentially how you get to the answers. Thank you for watching.